Now it's time to wrap up our unit on motion, so let's do a quick review. First of all, let's talk about coordinate systems. We just covered these. We've got spherical coordinate systems, Cartesian coordinate systems in 3D and in 2D, cylindrical coordinate systems, and polar coordinate systems. Wow! Really, let's just keep in mind our 2D Cartesian system. Here's our nice coordinate grid. We can specify any point by giving an x and a y coordinate. As you might remember, the x-coordinate is the distance along the x-axis, and the y-coordinate is the distance along the y-axis. Let's give it a shot. How about we have a point right here? Our distance along the x-axis is -1, so we make our ordered pair -1, and we've got a distance along the y-axis of -1 as well, so this is our ordered pair, -1, -1. Let's move on to motion. Motion is a change in position, which occurs over some period of time. This is the process of getting from A to B. Motion usually involves some kind of a rate with respect to time, which we'll talk more about in a few seconds. How about quantifying changes in position? Remember, we've got two different quantities here, distance and displacement. Distance is a scalar, whereas displacement is a vector. So what does this mean? Distance as a scalar only has magnitude. Displacement as a vector only has magnitude and is direction. This also means that distance is concerned with the entire path, no matter how crazy it is. Displacement, on the other hand, is concerned only with the start and the end points, A and B, and the shortest distance between them. This can make our calculations a lot simpler, but we have to remember to include a direction when we talk about displacement. Let's do a quick problem. Let's say Mr. Green Blob is at position 0. He, squirms or whatever along to position 4. Then he moves backwards to position 2. What distance does he travel? Wow, distance. Having some spelling troubles. Well, let's calculate this. He starts at 0, goes to 4. 4 minus 0 equals 4. Let's account for the second leg of his journey. Starts at 4, moves to 2. So 2 minus 4 equals -2. But since we're talking about distance, we don't care about direction or this negative sign. Let's add them up. 4 plus 2 is 6. That's perfect. Let's try displacement. That's a long word. Alright, if you can read that. We're only worried here about his starting point and ending point. So 0 and 2. His final position 2 minus initial position 0 is 2. And we'll notice that he moves in this direction, which is to the right. So 2 units right. This is displacement. How about velocity? Can you remember the equation for velocity? Velocity is the change in position, x, over the change in time, t. Let's think about the last problem. His displacement was 2 units right. Let's say he makes this displacement in 1 second. Then we have 2 units over 1 second equals 2 units per second. How about acceleration? You might remember that acceleration is the change in velocity over the change in time. Remember that this little Greek letter delta stands for change in. Alright, let's say that he makes transition from 2 units per second from rest in 1 second. Then his change in velocity is 2 units per second over 1 second, which gives us an acceleration of 2 units per second squared. These units are probably meters, since that's what we talk about most of the time in physics. Let's do some simple kinematics. This is just shuffling equations around. We've got V equals change in position over change in time, which we can rearrange to say that the change in position equals the velocity times the change in time. This is handy when we know velocity and time and want to find out position. So acceleration is change in velocity over change in time. We can rearrange this similarly, so we have that the acceleration times the change in time is equal to the change in velocity. This is also handy. Of course, we can't forget reference frames. Let's say we've got our buddy resting here on a park bench, and we've got a T-Rex sitting on a Ferrari, which is accelerating from 0 to 60 in 6 seconds. Which reference frame do you think is best? If you picked this guy's reference frame, you're in good shape. His reference frame is inertial because he's not undergoing any acceleration. The Ferrari's reference frame is non-inertial, so we don't like it. That wraps up our review of motion. Catch you for the exercises.